It begins with something smaller than a grain of sand. Imagine holding it in your palm. Dull, heavy, unremarkable. It doesn't glow. It doesn't hum. It looks like nothing more than a sliver of dark rock, the kind you might kick aside on a hike without a second thought. But this tiny fragment contains a secret older than mountains, older than oceans, older than life itself. Hidden inside it is a force so immense that, if unleashed, it could light an entire city for a year or erase it in less time than it takes to blink. This is uranium. Not the enriched kind, not the weaponized kind, just raw, natural uranium as it comes from the earth. And yet, even in this quiet, untouched state, it carries within it the echo of dying stars. Because uranium was never meant to be here. Not really. It didn't form when our planet cooled from a molten ball of rock. It was forged far away, long before the sun ever ignited. Born in the final, furious moments of stars so massive they couldn't survive their own gravity. When those stars exploded, they didn't just scatter light across the void. They scattered atoms, heavy and unstable, flung into the cold dark like cosmic seeds. One of those seeds was uranium. For billions of years, it lay dormant in the crust of our young world, buried under layers of stone and time. Humans walked past it for millennia, never knowing. Then, in the 20th century, we learned to listen, and what we heard changed everything. Because uranium isn't just heavy, it's restless. Its atoms are unbalanced, teetering on the edge of collapse. Left alone, they decay slowly, whispering radiation into the silence over eons. But if you strike one just right, with a single well-placed neutron, it doesn't just fall apart, it shatters. And in that shattering, it releases not only energy, but more neutrons, which strike other atoms, which shatter too, in a chain reaction that can either warm a hospital or release energy far beyond conventional reactions. But here's the catch. Not all uranium can do this. In fact, almost none of it can. Natural uranium is like a forest where only 1 in every 100 trees can burn. The rest just stand there damp and inert. To make a fire, whether for warmth or for war, you must find a way to gather only the flammable trees. You must separate them from the rest. And that process, so delicate, so precise, so fiendishly difficult, is called enrichment. It sounds technical. Bureaucratic even. But enrichment is where the cosmic story meets the human one. It's the threshold between potential and power, between peace and peril. A single enrichment facility can draw intense international attention due to its global significance. Such sites are closely monitored worldwide for safety and transparency. It's why a metal you've never seen can determine whether the world sleeps soundly or holds its breath. This isn't just about physics, it's about choice, about trust, about the terrifying moment when a species discovers it, can tap into the same forces that light the stars, and must decide whether to use that fire to cook bread or burn down the kitchen. And it all starts with that one grain of sand, heavy in your hand. Silent, ancient, waiting. You might think the story belongs in a government briefing room or a nuclear engineering textbook. But look closer. Trace the atoms back far enough, and you'll find them in the heart of a collapsing star, in the collision of 2 dead suns spiraling into each other, in the golden flash of a kilonova brighter than a billion suns. That's where uranium was born. That's the true origin of the fire we now hold. So this isn't a detour from the cosmos, it's a homecoming. Because the drama of uranium enrichment isn't just happening in centrifuges and control rooms. It's the latest chapter in a story written across the universe, in supernovae, in neutron stars, in the very fabric of matter. And now, for the first time in cosmic history, the outcome of that story depends not on gravity or entropy, but on us. That's why it's a big deal. Not because of politics, not because of weapons, but because it reveals something profound, that the universe has given us the keys to its inner workings. And with those keys comes a question we can no longer avoid. What kind of species are we? The answer begins not in a lab, but in the stars. And it ends wherever we choose. Long before humans walked upright, before the first fish crawled onto land, before Earth even had an atmosphere worth breathing, uranium was already here. Not as a human invention, not as a Cold War relic, but as a cosmic heirloom, delivered to our planet in the chaos of creation itself. The story of uranium begins not in a mine or a reactor, but in the violent twilight of massive stars. Picture a star at least 8 times heavier than our Sun. For millions of years, it burns steadily, fusing hydrogen into helium, then helium into carbon, oxygen, silicon, each step releasing energy, each layer nesting inside the one before, like an onion of fire. But fusion can only go so far. Once the core turns to iron, the star hits a dead end. Iron doesn't release energy when fused, it consumes it. And just like that, the engine stalls. Gravity, patient and relentless, seizes its chance. In less than a second, the core collapses inward at nearly a quarter the speed of light. Electrons and protons are crushed together into neutrons. The outer layers of the star, suddenly unsupported, slam into this newborn neutron core and rebound in a cataclysm so violent it rips the star apart. This is a core collapse supernova, one of the most energetic events in the universe. For a few fleeting weeks, it outshines its entire galaxy. And in that inferno of neutrons, protons, and unimaginable pressure, something extraordinary happens. Atomic nuclei, already heavy with iron, are bombarded by a flood of free neutrons. They absorb them faster than they can decay, a process scientists call the rapid neutron capture process, or R process. In minutes, atoms climb the periodic table, leaping from iron to zinc, to silver, to gold, to lead, and beyond. To uranium, to plutonium, to elements so heavy and unstable they barely hold themselves together. For decades, this was theory, beautiful, elegant, but unproven. Then, on August 17, 2017, everything changed. 2 neutron stars, each the collapsed remnant of a dead sun, each denser than an atomic nucleus, spiraled toward each other after orbiting for billions of years. In their final moments, they merged in a flash of gravitational waves and light. Telescopes around the world watched as the kilonova that followed glowed with the unmistakable signature of freshly forged heavy elements. Spectroscopic analysis confirmed it. Gold, platinum, and yes, uranium were being created in real time, right before our eyes. That single event, 130 million light-years away, solved a mystery that had lingered since the dawn of nuclear physics. Uranium wasn't made in quiet stellar furnaces. It was forged in cosmic collisions so rare and so violent that, over the entire history of the Milky Way, perhaps only a few dozen have occurred nearby enough to seed our solar neighborhood with these heavy atoms. When our solar system began to form 4.6 billion years ago, it coalesced from a cloud of gas and dust already sprinkled with stardust from ancient supernovae and neutron star mergers. Uranium was part of that mix. As Earth accreted from this primordial debris, uranium sank into the mantle and crust, trapped in minerals like uraninite and pitchblende. It was there, quietly decaying long before life emerged. Humans didn't discover uranium until relatively recently. In 1789, a German chemist named Martin Klaproth was analyzing a strange black mineral from a silver mine in Joachimshall, now in the Czech Republic. He isolated a new Earth, which he named after the newly discovered planet Uranus. He thought he'd found a new element, but what he actually held was uranium oxide. The pure metal wouldn't be isolated until 1841 by French chemist Eugène Melchior Péligeot. For over a century, uranium was little more than a curiosity. Its main use was as a yellow pigment in pottery glazes and tinting glass, giving Victorian-era vases a faint greenish glow under ultraviolet light. It was heavy, slightly toxic, and faintly radioactive, but no one knew why. That changed in 1896. Henri Becquerel, a French physicist, was studying phosphorescence, the glow some materials emit after exposure to sunlight. He wrapped photographic plates in black paper, placed uranium salts on top, and set them in the sun, expecting the sunlight to energize the uranium and expose the plates. But Paris had cloudy weather. Frustrated, he stored the setup in a drawer. Days later, he developed the plates anyway and found they were fogged. The uranium had exposed them without any sunlight at all. Something inside the uranium was emitting invisible rays. Becquerel had accidentally discovered radioactivity. This revelation electrified the scientific world. Marie Skłodowska-Curie, working with her husband Pierre, took up the investigation. She tested pitch blender and found it was far more radioactive than pure uranium could explain. There had to be other, even more active elements hidden within. In 1898, she announced the discovery of two new elements, polonium and radium. She coined the term radioactivity, and in doing so, opened a door into the atom's hidden heart. Yet even then, no one imagined uranium could be a source of usable energy. To most scientists, radioactivity was a slow, passive decay, a curiosity of nature, not a power source. The energy released was real, but minuscule, spread over thousands of years. It seemed useless for anything but medical experiments or glowing watch dials. That changed in the winter of 1938. In a Berlin laboratory, chemist Otto Hahn and his assistant Fritz Strassmann were bombarding uranium with neutrons, hoping to create new, heavier elements, what they called transuranics. But their results made no sense. Instead of heavier atoms, they kept finding barium, a much lighter element roughly half the size of uranium. Puzzled, Hahn wrote to his longtime collaborator Lise Meitner, a Jewish physicist who had fled Nazi Germany and was now in exile in Sweden. Meitner, walking in the snow with her nephew Otto Frisch, a physicist himself, pondered the data. Suddenly, it clicked. What if the uranium nucleus wasn't just chipping or growing, but splitting, like a droplet of water becoming unstable and dividing into two smaller droplets? Using Niels Bohr's liquid drop model of the nucleus, they calculated that when a uranium atom absorbed a neutron, it could become so unstable that it split into two lighter nuclei, releasing a burst of energy and additional neutrons. Frisch coined a term. For it, fission borrowed from biology, where cells divide. They estimated the energy release using Einstein's famous equation E equals mc squared. The mass of the fission fragments was slightly less than the original uranium nucleus. That missing mass had been converted directly into energy, about 200 million electron volts per fission. Compared to chemical reactions like burning coal, which release a few electron volts per molecule, this was a difference of tens of millions of times. In January 1939, Meitner and Frisch published their explanation. Within weeks, labs across the world confirmed it. Uranium fission was real. And with that confirmation came a chilling realization. Those extra neutrons released in fission could strike other uranium atoms, causing them to split too. A chain reaction was possible. If controlled, it could generate steady heat, enough to boil water, spin turbines, power cities. If uncontrolled, it could unleash a power that reshaped human history. But there was a problem. A big one. Natural uranium is mostly one isotope, uranium-238, over 99% of it. Only about 0.7% is uranium-235, the isotope that readily undergoes fission with slow neutrons. Uranium-238, by contrast, tends to absorb neutrons without fissioning, poisoning the chain reaction. So, unless you could somehow increase the concentration of uranium-235, unless you could enrich the uranium, you couldn't sustain a chain reaction. Not for a reactor, not for a bomb. And that, suddenly, made enrichment not just a chemical curiosity, but the key to the atomic age. The race was on. Not just to understand fission, but to separate the rare fissile atoms from the abundant inert ones. To do what nature never did, concentrate the fire of dying stars into a form humanity could wield. And in that moment, uranium stopped being just a mineral. It became a threshold, a test, a mirror held up to civilization itself. The cosmic gift had arrived. Now, we had to decide what to do with it. Imagine you're handed a bucket filled with 100 marbles. 99 of them are grey, smooth, ordinary, inert. But one is red, slightly smaller, slightly lighter, and if you tap it just right, it explodes with enough force to shake the room. Your task: separate that single red marble from the 99 grey ones, not by sight because they all look identical, not by touch because they feel the same. You can't even weigh them one by one. They're too small, too numerous. Now imagine you have to do this, not with a bucket, but with tons of material. And instead of marbles, you're dealing with atoms so tiny that a single grain of salt contains more of them than there are stars in the Milky Way. This is the essence of uranium enrichment. At the heart of the problem lies a truth so subtle it defies. Intuition, uranium-235, and uranium-238 are chemically identical. They bond the same way, react the same way, dissolve the same way. If you mix them into a solution, no chemical test could tell them apart. The only difference between them is mass, 3 neutrons worth. Uranium-235 has 143 neutrons in its nucleus. Uranium-238 has 146. That's it. A difference of less than 1% in total atomic weight. But that tiny difference is everything, because in the delicate dance of nuclear fission, only uranium-235 readily splits when struck by a slow-moving neutron, the kind easily produced in a reactor. Uranium-238, slightly heavier, tends to absorb fast neutrons without fissioning, or simply ignore slow ones altogether. So if you try to build a chain reaction with natural uranium, where uranium-235 makes up less than 1%, the neutrons get lost, absorbed, or scattered before they can find another fissile atom. The fire sputters out. To keep it burning, you need to tip the odds in your favor. For a nuclear power plant, you typically need uranium enriched to between 3 and 5% uranium-235, still mostly uranium-238, but enough fissile material to sustain a steady, controlled reaction. For a nuclear weapon, you need over 90% almost pure uranium-235. That's weapons grade. The challenge then isn't finding uranium. It's everywhere, in granite, in seawater, in the soil beneath your feet. The challenge is separating atoms that refuse to be told apart by any means except weight. And because atoms are unimaginably small, you can't just put them on a scale. You need a method that exploits that minuscule mass difference again and again, trillions of times over, until the concentration shifts from a whisper to a shout. This is why enrichment is hard. Not because it's conceptually mysterious, it's just physics, but because it demands industrial-scale precision operating at the edge of what's physically possible. It's like trying to sort grains of sand by weight using only the wind. Early scientists knew this would be the bottleneck. In 1939, as the reality of fission sank in, physicists like Leo Szilard and Enrico Fermi warned the USS government that if Nazi Germany figured out how to enrich uranium, they could build an atomic bomb. But how? The methods available at the time were crude, slow, and wildly inefficient. One idea was gaseous diffusion. Turn uranium into a gas, uranium hexafluoride, a volatile compound that forms when uranium reacts with fluorine, and pump it through a porous barrier. Because uranium-235 is slightly lighter, its molecules move a hair faster and are very slightly more likely to pass through the microscopic holes in the barrier than the heavier uranium-238 molecules. But the difference is so small that a single pass barely changes the concentration. To go from 0.7% to 90%, you'd need thousands of stages, each one feeding into the next, each one requiring massive pumps, corrosion-resistant materials, and staggering amounts of electricity. Another idea was electromagnetic separation, essentially building a giant mass spectrometer. Ionize uranium gas, accelerate the ions through a magnetic field, and watch them curve. Lighter ions bend more sharply than heavier ones, so uranium-235 and 238 land in slightly different spots. You could then collect them separately, but this method is incredibly slow. It processes atoms one by one, like picking rice grains with tweezers. During the Manhattan Project, the US built a facility called Y-12 in Oak Ridge, Tennessee, filled with massive calutrons, a blend of California University and cytotron. It consumed 10% of all electricity in the United States at the time, and produced only enough enriched uranium for one bomb after 2 years of operation. Then there was centrifugation. A concept so elegant it seems almost obvious in hindsight. Spin uranium hexafluoride gas in a cylinder at incredible speeds, 50,000 to 100,000 revolutions per minute. Centrifugal force pushes the heavier molecules toward the outer wall, while the lighter ones cluster near the center. A gentle scoop at the center draws off gas slightly enriched in uranium-235. Another at the edge draws off depleted gas. Like cream rising in milk, but driven by rotation instead of gravity. The problem? Building a centrifuge that could spin that fast without tearing itself apart. The materials had to be strong, perfectly balanced, and resistant to the corrosive uranium hexafluoride gas. In the 1940s, no one could do it reliably. The US abandoned centrifuges early in the Manhattan Project, betting instead on gaseous diffusion and calutrons. But others didn't give up. In the Netherlands, a German-born physicist named Gernot Zipper was captured by the Soviets after the war and forced to work on their nuclear program. There, he helped refine the centrifuge design into something practical. After his release in the 1950s, he brought the knowledge to the West. By the 1960s, centrifuge enrichment was not only feasible, it was vastly more efficient than gaseous diffusion, using only about 1/20th the electricity. Today, over 90% of the world's enriched uranium is produced by centrifuges. Cascades of them, thousands linked in series hum, quietly in vast windowless halls, spinning day and night, slowly concentrating the rare isotope atom by atom. But here's what makes enrichment so politically charged. The same machine that produces fuel for a nuclear power plant can, with time and reconfiguration, produce material for a bomb. There's no technical bright line. A civilian enrichment plant running at 3% can be reconfigured to run at 90%. The hardware doesn't change, only the operating parameters and the duration. That's why enrichment is the fulcrum of nuclear diplomacy. It's not the uranium itself that's dangerous, it's the capability to concentrate it. Once a nation masters enrichment, it holds the latent power to build a weapon, even if it claims peaceful intentions. And because centrifuges are relatively compact and energy efficient, they can be hidden underground, shielded from satellites, disguised as ordinary industrial sites. This ambiguity is the heart of the tension. Enrichment sits at the crossroads of energy and annihilation, of progress and peril. It's not magic, it's engineering. But it's engineering that deals in the currency of stars, and the consequences are measured in cities. And that's why, even today, the quiet whir of a centrifuge can echo louder than a thunderclap in the halls of power. In the quiet hills of Tennessee, in the early 1940s, the United States embarked on an industrial endeavor unlike any the world had seen. It wasn't building tanks or planes. It was trying to separate atoms, trillions upon trillions of them, by a difference so small it defied imagination. This was the heart of the Manhattan Project's mission, to concentrate the rare isotope uranium-235 from its far more common cousin, uranium-238, and to do it not in grams but in kilograms. Enough to fuel a new kind of explosion, one born not from chemistry, but from the nucleus itself. They didn't know which method would work. So they tried them all, on a scale that bordered on the mythic. First was gaseous diffusion. Scientists turned uranium into a volatile gas, uranium hexafluoride, and pumped it through a series of barriers pierced with microscopic pores. Because uranium-235 is slightly lighter, its molecules moved a fraction faster and were ever so slightly more likely to slip through the holes. But the effect was minuscule. A single pass changed the concentration by less than 1%. To reach weapons-grade purity, the gas had to pass through thousands of stages, each one feeding into the next in a cascade that stretched for miles inside a single building. The K-25 plant, the largest in the world under one roof at the time. It consumed electricity like a small country, its cooling towers exhaling steam into the Appalachian sky, while inside, an invisible sorting of stardust was underway. Then came the calutrons, massive electromagnetic separators housed in the Whitewell facility. Here, uranium was vaporized, ionized, and hurled through a vacuum chamber wrapped in powerful magnets. The magnetic field bent the paths of the ions into arcs. Lighter uranium-235 curved more sharply than uranium-238, landing on separate collectors. But the beams were unstable, the machinery temperamental. Much of the fine-tuning was done by young operators, many of them women who watched dials and adjusted knobs without knowing what they were enriching. They called themselves the Calutron Girls. Their hands, guided only by instinct and instruction, helped coax the first significant quantities of enriched uranium into existence. Years later, when they learned what they'd helped create, many spoke not of pride, but of awe and sorrow at the power they'd unknowingly shaped. A third path was explored but abandoned, the gas centrifuge. The idea was elegant. Spin uranium hexafluoride gas at incredible speeds and let centrifugal force push the heavier molecules outward while the lighter ones gathered near the center. But in the 1940s, materials science wasn't ready. Rotors shattered under stress. Bearings failed. The technology seemed too fragile for wartime urgency. So the project doubled down on brute force diffusion and collutrons, succeeding, but at enormous cost in resources, time, and energy. Meanwhile, across the globe, another scientific effort was unfolding. In the Soviet Union, physicists aware that the Americans were racing toward a bomb launched their own program. They too faced the enrichment challenge. Lacking the industrial capacity for massive diffusion plants, they focused on alternative approaches. Soviet scientists refined centrifuge design through relentless experimentation, developing rotors that could spin longer and faster without disintegrating. By the early 1950s, they had built working prototypes that proved far more efficient than diffusion. This wasn't espionage, it was parallel discovery, driven by the same laws of physics that governed atoms everywhere in the universe. The breakthrough that would change everything came not from a single nation, but from the universal language of engineering. Researchers across the world realized that if you could build a centrifuge strong enough to spin uranium hexafluoride at 50,000 revolutions per minute, or even 100,000, without tearing itself apart, you could achieve in one machine what took thousands of diffusion stages. The key was in the materials: high-strength alloys, precision-balanced rotors, vacuum-sealed chambers to reduce friction. Once those hurdles were overcome, centrifuges became the most energy-efficient way to enrich uranium, using only a fraction of the power required by older methods. This shift had profound implications. Enrichment no longer demanded city-size factories and national grids. It could be done in smaller, modular facilities, still complex, still demanding advanced engineering, but far more accessible than before. And because the physics was now well understood, the knowledge spread through scientific journals, university labs, and international conferences. The genie, in a sense, was out of the bottle, not as a secret, but as a shared human capability. But here's what made enrichment uniquely challenging. The same machine that produces low-enriched uranium for a power plant can, in principle, be reconfigured to produce highly enriched uranium for a weapon. There is no physical switch that says peace or war. The difference lies only in how long you run the cascade, how you connect the pipes, and where you collect the output. This isn't a flaw in the technology, it's a consequence of nature itself. Uranium-235 is fissile, whether it's in a reactor core or a warhead. The atom doesn't care. This duality became the central puzzle of the nuclear age. How do you allow humanity to benefit from the atom's energy? Clean, dense, carbon-free, while ensuring that the same process isn't used to build weapons. The answer wouldn't come from politics alone, but from science itself. Scientists and engineers began designing systems to make enrichment transparent. Tamper-proof seals, continuous radiation monitors, environmental sampling for trace isotopes. These became the tools of verification. The goal was to turn enrichment facilities into open books, where every gram of material could be accounted for, not through trust alone, but through measurable, repeatable physics. In this way, the story of enrichment shifted from one of secrecy to one of observation, from hiding atoms to watching them. And that shift reflected a deeper truth. In a universe governed by immutable laws, the only sustainable path forward is one built on shared understanding, not suspicion. The machines kept spinning. But now, they spun not just to separate isotopes, but to separate fear from fact, myth from measurement, and hope from hubris. And in that hum, a new kind of human ingenuity was being tested, not just how to split the atom, but how to live with the knowledge, so that we can. At the heart of uranium enrichment lies a quiet paradox, one that has shaped the nuclear age not through drama, but through design. The same physical process that can generate electricity for millions can, in principle, produce material for a weapon. Not because of malice, but because of physics. The atom does not distinguish between a reactor core and a warhead. It only responds to neutrons, mass, and energy. And that neutrality is both a gift and a burden. To understand this duality, we must first understand the numbers, not as political thresholds, but as scientific ones. Natural uranium contains about 0.7% uranium, 235. That's not enough to sustain a chain reaction in most reactor designs. But if you enrich it to between 3 and 5%, just a few atoms more per thousand, you create fuel that can power a nuclear plant for years. This is called low-enriched uranium. It cannot explode. It's as incapable of a nuclear detonation as a damp log is of becoming a wildfire. The concentration of fissile atoms is simply too low to support the runaway chain reaction required for a bomb. Weapons-grade uranium, by contrast, is enriched to over 90% uranium-235. At that level, the atoms are so densely packed with fissile potential that a single neutron can trigger an exponential cascade, releasing the energy of thousands of tons of TNT in microseconds. The difference between 3% and 90% isn't just a matter of degree. It's the difference between a controlled burn and a detonation. But here's the crucial point. The machines that produce 3% can, with time and reconfiguration, produce 90%. There is no magical barrier in the hardware. A centrifuge doesn't know what level it's enriching to. It simply spins, separates by mass, and outputs a slightly enriched stream. To go from reactor fuel to weapons material, you don't need new machines. You need more time, more cascades, and a different plumbing setup. This is what scientists call a dual-use technology. Not because it's sinister, but because its application depends entirely on human intent. Like fire, like electricity, like rocketry, it can illuminate or incinerate. The challenge isn't the physics. It's how we, as a species, manage the knowledge. After the Second World War, as nuclear technology began to spread, the global scientific community recognized this dilemma. They understood that banning enrichment outright would deny humanity access to a powerful source of clean energy. But allowing it without oversight risked a world where any determined group could, in theory, cross the threshold to weapons. The solution wasn't political. It was scientific. In 1957, the International Atomic Energy Agency was created, not as a police force, but as a body of scientists, engineers, and inspectors dedicated to one mission, verifying that nuclear material is used only for peaceful purposes. Its tools aren't treaties or threats, but instruments of measurement. Gamma spectrometers that detect the unique energy signatures of isotopes. Mass spectrometers that can identify uranium enriched to the 0.1%. Environmental swipes that pick up invisible traces of particles from weeks or months prior. Even the heat signatures of centrifuge halls can be monitored by satellite-based infrared sensors. Every enrichment facility that operates under international safeguards becomes a kind of open laboratory. Seals are placed on valves and pipes designed to break if tampered with. Cameras record activity continuously. Material accountancy tracks every gram of uranium as it moves through the process, like a cosmic ledger written in atoms. If even a small amount goes missing, the anomaly shows up in the data. This system isn't perfect, but it's rooted in the same principles that govern stars and supernovae: observation, repeatability, and the unbreakable laws of nature. You can lie with words, but you can't lie with isotopes. Uranium-235 always emits the same radiation. It always has the same mass. It always behaves the same way under a magnetic field. In a world full of uncertainty, the atom remains honest. And that honesty has enabled something remarkable. Over 30 countries today operate nuclear power reactors fueled by enriched uranium, without ever pursuing weapons. They do so under transparent, science-based verification. Their scientists collaborate openly, their data is shared, their facilities are visited by international peers. In these places, enrichment is not a secret, it's a service, like refining oil or purifying water, but for the atomic age. Even the fuel itself can be designed to reduce risk. Some reactor fuels are blended with isotopes that make them extremely difficult to re-enrich or divert. Others use fuel assemblies that are physically sealed and can't be opened without detection. Research continues into proliferation-resistant fuel cycles, ways to use nuclear energy while making weaponization practically impossible, not just politically discouraged. This is the quiet triumph of the peaceful atom, that we've learned to harness a force. Born in dying stars, not for destruction, but for light, heat, and healing. Nuclear medicine uses isotopes to diagnose cancer. Nuclear power provides steady electricity without burning fossil fuels. And all of it begins with the same process, enriching uranium one atom at a time. But the responsibility never disappears, because the moment you master enrichment, you hold a latent capability, the knowledge that, if you chose to, you could cross that line. And that's why the real test isn't technical, it's ethical. It's not about whether we can enrich uranium. We've known that since the 1940s. It's about whether we should, and how we ensure that the fire we've inherited from the stars is used to warm, not to wound. In the end, the dual nature of enrichment isn't a flaw in the universe. It's a mirror. It shows us what we value, what we protect, what we're willing to share, and what we're wise enough to restrain. And in that reflection, we see not just atoms, but ourselves. As the knowledge of uranium enrichment spread beyond the laboratories of the mid-20th century, a new kind of architecture began to rise, not of steel and glass, but of trust, transparency, and shared scientific understanding. This architecture wasn't built with bricks, but with protocols, instruments, and a simple, powerful idea that the same laws of physics that allow us to split the atom can also help us verify how it's being used. This is the story of how humanity chose to live with the fire, not by hiding it, but by watching it together. After the first nuclear weapons were developed, scientists around the world understood that the genie could not be put back in the bottle. The physics was out. The equations were published. The principles of fission and enrichment were now part of the human inheritance. The question was no longer whether others could learn to enrich uranium. It was whether they would choose to do so openly, under scrutiny, and for peaceful ends. The answer came not through force, but through a global scientific covenant. In the decades following World War II, a framework emerged, not dictated by any single nation, but shaped by physicists, chemists, and engineers from dozens of countries who shared a common language, the language of measurement. They agreed that if nuclear technology was to benefit all of humanity, its use had to be verifiable, not by promises, but by data. Not by politics, but by particles. At the center of this effort stood the International Atomic Energy Agency, the IAEA, a unique institution where inspectors carry Geiger counters instead of guns, and where the most powerful tool is not a sanction, but a spectrometer. Imagine walking into an enrichment facility today. What you'd see isn't a fortress, but a highly instrumented industrial plant. Along every pipe, on every valve, are tamper-indicating seals, small devices that record any attempt to open or reroute the flow. Cameras stream footage to secure servers. Air samplers continuously pull in microscopic particles, which are later analyzed in labs to detect even trace amounts of enriched uranium. If someone tried to divert material, the isotopic signature would betray them. Not weeks later, but often in real time. This isn't surveillance in the political sense. It's scientific due diligence, like calibrating a telescope or checking a particle detector. The goal isn't to accuse, but to confirm. And because the methods are based on universal physics, they're accepted across borders. A gamma ray emitted by uranium-235 in Tokyo has the same energy as one in Toronto or Tunis. Science doesn't take sides. Over time, this system enabled something extraordinary. Countries with no nuclear weapons chose to develop nuclear energy anyway, confident that they could do so transparently and that the world would see their peaceful intent. Argentina, Brazil, Japan, South Korea, the United Arab Emirates, all built enrichment or fuel fabrication capabilities under full IAEA safeguards. Their scientists publish papers. Their regulators attend international conferences. Their facilities host peer reviews. In these places, nuclear technology isn't a symbol of power. It's a public utility, like a hydroelectric dam or a solar farm, but operating at the atomic scale. Even the fuel cycle itself has evolved to support this transparency. Many nations don't enrich uranium at all. Instead, they buy fuel from international suppliers, guaranteed to meet strict purity and enrichment standards, and return the spent fuel for secure storage. This cradle-to-grave model removes the need for every country to master the full enrichment process, reducing both cost and risk. It's like leasing a battery instead of mining lithium yourself, efficient, safe, and traceable. And for those that do enrich, new technologies are making verification even more robust. Laser-based enrichment methods, though still experimental, offer the potential for more precise control and easier monitoring. Digital monitoring systems now use blockchain-like ledgers to record every movement of nuclear material, creating an immutable chain of custody written in code and physics. Even the heat and power signatures of centrifuge halls can be cross-checked against declared operations using satellite data. But perhaps the most profound shift has been cultural. In the early days of nuclear science, secrecy was the norm. Today, openness is the standard. Young scientists from dozens of nations train together at IAEA workshops. Laboratories share calibration standards. Data from environmental sampling is compared across continents to ensure consistency. This isn't idealism, it's practicality. Because in a world where a single gram of diverted material could, in theory, matter, the only reliable shield is collective vigilance. This global scientific ecosystem doesn't eliminate risk, but it transforms it from a matter of suspicion into a matter of measurement. Instead of asking, can we trust them? The question becomes, what does the data say? And because atoms never lie, the answer is always knowable. In this way, uranium enrichment has become more than a technical process. It's a test of our capacity for cooperation, a demonstration that even the most powerful knowledge can be shared if we build the right safeguards, not just in steel and concrete, but in norms, in training, in mutual respect for the scientific method. And that, perhaps, is the quiet miracle of the peaceful atom, that we've learned to handle a force born in stellar explosions, not as a weapon of dominance, but as a shared responsibility, monitored not by spies, but by scientists, secured not by walls, but by wavelengths. The fire from the stars is in our hands. And for the first time in history, we're learning to tend it, not alone, but together. The story of uranium enrichment is far from over. In fact, it's entering a new chapter 1, shaped not by the urgency of war or the tensions of the Cold War, but by the quiet hum of innovation and the pressing needs of a changing planet. As we look to the future, the same scientific ingenuity that once split the atom is now being turned toward making its use safer, cleaner, and more transparent than ever before. One of the most promising frontiers is in the design of nuclear reactors themselves. Traditional reactors rely on low-enriched uranium, typically between 3 and 5% uranium, 235. But new generations of reactors are being developed that could drastically reduce or even eliminate the need for enrichment altogether. Take thorium, for example. Unlike uranium, thorium is not fissile on its own, but when placed in a reactor, it can be transformed into uranium-233, which is. Thorium is more abundant than uranium, produces less long-lived radioactive waste, and, critically, is far more difficult to weaponize. Because the byproducts include isotopes that emit high levels of gamma radiation, handling the material would be extremely hazardous to anyone trying to create a device demonstrating unprecedented energy release. In this way, the physics itself becomes a barrier to misuse. Then there are small modular reactors, compact factory-built units that can be deployed in remote areas or integrated into existing power grids. Many of these are designed to run for decades without refueling, using sealed cores that are returned to the manufacturer at the end of their life. No on-site fuel handling, no enrichment infrastructure, no opportunity for diversion. It's nuclear energy made as simple and secure as a battery. Even the process of enrichment is evolving. Laser enrichment, a technique that uses precisely tuned lasers to excite only uranium-235 atoms, allowing them to be separated chemically, has long been a theoretical possibility. Recent advances suggest it could one day be far more energy efficient than centrifuges. But here's the twist. Because laser enrichment leaves a distinct isotopic signature, it may actually be easier to detect and verify than traditional methods. Once again, science offers not just a new tool, but a new way to ensure accountability. At the same time, artificial intelligence and machine learning are being applied to nuclear safeguards. Algorithms can now analyze data from radiation sensors, power consumption logs, and satellite imagery to detect anomalies that might indicate undeclared activity. These systems don't replace human inspectors, they empower them, turning terabytes of raw data into clear, actionable insights. It's like giving every safeguard officer a pair of eyes that never blink and a memory that never fades. But perhaps the most profound shift isn't technological, it's generational. Today's nuclear scientists aren't working in secret bunkers. They're collaborating across borders on open-source simulation software, publishing in peer-reviewed journals, and teaching students from every continent. They see nuclear technology not as a symbol of power, but as a tool for sustainability, a way to provide carbon-free energy in a world racing to outrun climate change. For them, the legacy of enrichment isn't just about the bomb. It's about the hospital powered by a reactor, the cancer treated with radioisotopes, the village lit by clean electricity. And yet, the fundamental truth remains: the atom is neutral. It doesn't care how we use it. That choice will always rest with us. But what's changing is our ability to make that choice wisely. Not through fear, but through knowledge. Not through isolation, but through shared understanding. The fire we inherited from supernovae and neutron star collisions is still in our hands. But now, we're learning to shape it not just with engineering, but with ethics, not just with centrifuges, but with conscience. And in that evolution, from secrecy to transparency, from suspicion to verification, from fear to stewardship, we may be witnessing something rare in human history: the maturation of a species that has learned to wield cosmic power, not as a weapon, but as a covenant. The future of enrichment isn't about who can do it, it's about how we choose to use it together. In the end, uranium enrichment is not really about machines, or isotopes, or even energy. It's about a single, quiet moment of human choice. Think back to that grain of uranium, dull, heavy, ancient, born in the death throes of a star that exploded long before Earth existed, carried across the galaxy on waves of light and dust, buried in rock for billions of years. Then, one day, unearthed by human hands, we could have left it there. We could have admired its weight, noted its faint warmth, and walked away. But we didn't. We listened. We probed. We split it open. And in doing so, we split our own future into two paths. One path leads to light, to cities powered without smoke, to hospitals diagnosing disease with invisible rays, to spacecraft journeying to the outer planets on nuclear batteries. The other leads to ash, to silence where voices once laughed, to shadows burned into stone, to fear that echoes across generations. The astonishing thing is that both paths begin with the exact same atom, the exact same physics, the exact same centrifuge spinning in the exact same way. The only difference is us. That's the true weight of enrichment. It's not a technical hurdle, it's a mirror. Every time we build a cascade of centrifuges, we're not just separating uranium-235 from uranium-238. We are separating our hopes from our fears, our wisdom from our ambition, our shared future from our worst impulses. And what's remarkable, what gives reason for hope, is that, so far, humanity has mostly chosen the path of light. Over 30 nations use nuclear technology peacefully. Thousands of reactors have operated for decades without incident. Millions of medical procedures happen every year thanks to isotopes born in the same process. The fire has warmed far more than it has burned. That doesn't mean the danger is gone. It never will be. As long as the physics exists, the choice remains. But we've built something fragile and beautiful in response, a global community of scientists who watch, measure, verify, not to control, but to protect. They don't carry flags. They carry spectrometers. And in their quiet work, they uphold a simple truth that knowledge once shared can be a shield as well as a sword. So the next time you look up at the night sky and see the glow of distant stars, remember this: the same forces that light those stars are here in our hands, not as a curse, not as a privilege, but as a responsibility passed down from dying suns, through stardust, through rock, through laboratories to us. And the question they whisper isn't about technology. It's about who we are and who we choose to become. It all comes back to that single grain, heavy in your palm, silent, older than life, forged in the heart of a dying star, delivered across the void, waiting in the dark until we learned how to listen. We could have left it buried, but we didn't. And in that choice to look deeper, to understand, to harness, we stepped into a new chapter of our story. Not as passive observers of the cosmos, but as participants in its unfolding. Uranium enrichment, for all its complexity, is really just a conversation with the universe. A dialogue written in neutrons and mass, in cascades and centrifuges, in equations and ethics. And the answer we keep receiving is this: power is neutral, meaning is ours to give. The same atom that lights a city can erase one. The same knowledge that heals can harm. The same fire that warms can consume. But here's what the stars never told us, because they couldn't. What we do with that fire is up to us. And so far, despite our fears, despite our mistakes, we have chosen, again and again, not perfection, but care. Not dominance, but stewardship. Not secrecy, but shared vigilance. That's the real wonder. Not the physics, not the machines, but the fact that a species born on a fragile world under a modest star has looked into the heart of matter and said, "We will handle this with humility." The journey from supernova to centrifuge is long, but the next step, the most important one, is only a whisper away. It's in the choice we make today, and tomorrow, and every day after. Because the fire from the stars isn't just in our reactors, it's in our hands and in our hearts.